Hello dear students, I hope you are enjoying the lectures of permutations and combination. Students, in our last lecture, we had studied till permutation. We had understood the meaning of the word permutation or arrangement of objects. Now, I will take up a few more examples and understand the word permutation in somewhat deep. And then we will move forward and understand what is the meaning of the word combination. What is the formula of combination of n distinct objects taken R at a time. Alright, so let's get started with the topic.
Now let us take another theorem which is based on permutation itself. In this lecture also we will discuss a bit more about permutations. Theorem 2 says number of permutations of n different objects taken are at a time where repetition is allowed. In our previous theorems we discussed about arranging n different objects taken are at a time, but there repetition of objects were not allowed. Now in this particular case repetition is also allowed. So how are we going to make permutations in this case? Let me tell you. First of all, you are going to mark how many places? R places, because we are taking R at a time out of n different objects. Alright, so I have marked R places. This is first place, this is second place, this is third place, and so on. This is rth place. Alright, so first place can be occupied by how many objects? In how many ways I can fill up this place? Now we have done it many a times that if we have total n distinct objects, then this place can be occupied in how many ways? N ways. Alright, second place can be occupied n again, because since repetition is allowed, the object that has been kept over here can be again kept over here. Alright, that is the meaning of repetition. So the first place can be occupied, can be filled up in n ways, and second place can also be filled up in n ways. Similarly, third place can also be filled in n ways, and fourth place can also be filled up in n ways, and this continues. And likewise the last place, that is the rth place, can also be filled up in n ways. So I think this is very simple type of permutation in which repetition is given to be allowed. So basically our net answer is going to be n multiplied by n multiplied by n multiplied by n, and so on. Now this multiplication of n is happening how many times? This is happening how many times? R times, because we had marked over here how many places? R places. So this is equal to n raised to the power r, because if I had multiplied n 2 times, I had got n square. If I had multiplied n 3 times, I had got n cube. So if I multiply n r times, what I am going to get is n raised to the power r. Alright, so the answer of this theorem of this case is going to be n raised to the power r. For example, if we have 5 distinct objects, and out of these 5 we are arranging 3 objects, then in how many ways this arrangement can be done such that repetition is allowed? Repetition of objects is allowed. So in this case what we are going to do is, how many objects are to be arranged? 3 objects. So I have marked 3 places. First place can be filled in how many ways? Total option 5. Second place can also be filled in how many ways? 5. Third place can also be filled in how many ways? 5. So the net answer comes out to be 5 multiplied by 5 multiplied by 5. Alright, so this comes out to be 5 raised to the power 3. And this is what our formula also says, that if we have n different objects and out of these n, r is taken at a time and r is taken and arranged, then when repetition is allowed, the total number of permutations is going to be n raised to the power r. So here in this example, what was the value of n? I had taken 5 objects, so n was equal to 5. And out of 5, how many I was trying to arrange? I was interested in arranging 3 objects, so r becomes 3. So answer directly can be given when repetition is allowed. The total number of arrangement is n raised to the power r and is equal to 5 raised to the power 3, which is 125. Alright, I hope you have understood theorem number 2. Theorem number 2 is different from theorem number 1, where repetition is allowed. Alright, but in theorem number 1, repetition was not allowed. There we had written NPR, and here we have written n raised to the power r. Alright, okay. Now I am completing the topic of permutation altogether, and then we will be taking examples and illustrations and questions of permutations. But let me first complete the theory of permutations. Now, one more important topic related to permutations, that is permutations of objects such that not all are distinct. Now, we are interested in arranging objects such that all the objects are not distinct. Not all are distinct. Some can be different and some can be same. For example, if you have 3 apples, 4 bananas and 5 mangoes, and you have to arrange all of them. You have to arrange all of them in a row. Now, 3 fruit here, 4 fruits here and 5 fruits here. They add up to give us 12 total fruits. So total fruits are 12. So if somebody asks you in how many ways these particular objects, these many objects can be arranged where 3 apples are same, 4 bananas are same and 5 mangoes are also same. So please don't say that answer is going to be 12 factorial. 12 factorial is going to be incorrect. Why? Because 12 factorial would have been the correct answer in case of distinct objects or different objects. But here some objects are of same kind. If the question says that the apples are not same, then we would have considered them to be different. Alright, but in this case it has been given that apples are same, bananas are same and mangoes are same. Fruits of same category are alike. So the answer is not going to be 12 factorial. Alright, answer is going to be different. So we have to understand that how do we arrange or how do we make permutations of objects if not all of them are distinct, as it is happening in this particular case. Alright, okay, let's study. The total number of objects be n. Alright, consider we have total number of objects equal to n. Now out of these n objects, p are alike of one kind, q are alike of second kind and r alike of third kind. This is similar example to what I have taken over here. Alright, here n equals to 12, p equals to 3, q equals to 4 and r equals to 5. So you can relate it with this example written over here. So again we have n objects out of which p are alike of one kind, q are alike of second kind and r of alike of third kind, and rest all, that is the remaining all, are different. Then the number of permutations of such objects will be equal to n factorial divided by p factorial q factorial r factorial. Alright, what I have written, the number of permutations in such case will be equal to n factorial divided by p factorial into q factorial into r factorial. It means if I were to answer this question in which I had given 12 total fruits, so n was 12, 3 apples were same, so p equals to 3, 4 bananas were same, so q equals to 4, because these are alike of one kind, these are alike of second kind, and 5 mangoes are same, so r equals to 5, these are alike of third kind. So according to this topic, I am writing n equals to 12, p equals to 3, q equals to 4, and r is equal to 5. So in how many ways they can be arranged? The number of arrangement will be equal to 12 factorial divided by 3 factorial into 4 factorial into 5 factorial. Alright, how to calculate it? I will teach you, but for now we should understand that this is our answer. Had the things been all distinct, if all the things were different, our answer would have been 12 factorial. Alright, but you must appreciate this fact that in this case, when things are not all distinct, in fact some of alike, in that case the answer is coming out to be 12 factorial divided by 3 factorial into 4 factorial into 5 factorial. This is quite interesting. Why is it happening? First thing we are observing is that our answer is coming out to be less than 12 factorial. Alright, it is not equal to 12 factorial first of all. Secondly, it is coming out to be less than 12 factorial. Now why is it happening? Let us understand. So consider we have 3 balls, out of which 2 are blue and 1 is green. Alright, I am trying to make you understand that why have we divided in this case 12 factorial with 3 factorial, by 3 factorial, 4 factorial and 5 factorial. Alright, I am trying to make you realize this. So consider we have 3 balls, out of which 2 are blue and 1 is green. And it is also given that balls of same colors are alike. It means that the two blue balls are alike. Alright, so we have n equals to 2, total 3 balls, p equals to 2, alike of one kind, and what we are left with is q, that is 1. Alright, this is the case. So if somebody asks you, how do you arrange these 3 balls? So let me write down each arrangement. Let me define the first blue ball as B1, second blue ball as B2, and third ball as G, which is green ball. Alright, I am considering the balls to be different. Consider the balls to be different. If balls were different, so I had written first ball as B1, second ball as B2, and third ball as G. Now, if I ask you in how many ways we can arrange these 3 balls, the answer would be simply 3 factorial, because we have 3 objects. Taking all at a time can be arranged in how many ways? 3 factorial ways. That is 6 ways. Now let us try to write each of these 6 cases. The first one is B1, B2, G. The second one is B2, B1, G. Alright, please make a note, when things are different, these arrangement will be considered as different. Alright, now third arrangement can be keep B1 over here and keep green ball in middle and then B2 over here. Fourth arrangement can be interchange B1 and B2 and keep the green ball in between. Last 2 arrangements can be green over here and then B1 over here and then B2, and finally we can have green ball over here and blue over here and then B1 over here. Alright, so these are total 6 arrangements if the things were different. If the things were different, that is b1 and b2 were different, then I would have arranged them in how many ways? 3 factorial, and this is equal to 6 ways, and those 6 ways are which we have shown. Alright, but now what is happening over here is these two blue balls of same colors are alike. Alright, so when things were different, I had written down this arrangement. But when these two blue balls of same colors are alike, we can say that B1 and B2 are same. If B1 and B2 are same, then this arrangement over here and this arrangement over here will not be counted as two arrangement. In fact, this will be one arrangement. Why? Because in this arrangement we have blue, blue, green, and this arrangement also tells us the position blue, blue and green. Alright, when things were different, then we said that in different order matters, in permutation order matters. So B1 B2 G and B2 B1 G were two different arrangements. But when things are alike, we are saying that this is also blue, this is also blue, and this is green. And in second case also, this is one is blue, this one is blue, and this is green. So basically I am saying same arrangement two times. So it doesn't make it two arrangements. The arrangement is going to stick to one. Alright. Similarly, these two arrangements are same and will be counted as one. Similarly, these two arrangements are same and they will be also counted as one. Why? Because here we are having green, blue, blue, and here also we are having green, blue, blue, if blue balls are same. In the middle two, we are having blue, green, blue, and this also says blue, green, blue. So if blue balls are of same kind, if blue balls are alike, we are saying that each case is repeating itself how many times? Two times. Students, each case is repeating itself. Each case is repeating itself how many times? Two times. And it is better to say that they are repeating themselves how many times? 2 factorial times, because 2 factorial is equal to 2. And now we can ponder over how this 2 factorial is occurring. Why this 2 factorial is occurring? Because out of these 3 objects, 2 are of same kind. That is why each case is repeating itself 2 factorial times. So when the things were distinct, our answer was 3 factorial. But we know when the things out of 3, if 2 are same, then this is not the correct answer. But correct answer can be obtained by dividing this quantity by what quantity? 2 factorial. Why? Because this answer was 2 factorial times original answer. So in order to get the correct answer, we have divided it by 2 factorial. And why only 2 factorial? Because 2 objects were of same kind. Alright, I have tried to demonstrate with this example that these two arrangements are same, these two arrangements are same, and these two arrangements are same, and that is why each case is repeating itself how many times? 2 factorial times. So the answer is not going to be 6 when 2 blue balls are same. In fact, it is 1 plus 1 plus 1, which is equal to 3. And 3 factorial divided by 2 factorial is also going to give you what? It is also going to give you 3. Alright, so in order to sum up, I can say that if you have 5 green balls, 3 red balls, and 4 blue balls. Alright, so total we have 5 plus 3 plus 4, that is equal to 12 balls. And out of these 12 balls, 5 green are of same kind, 3 red are of same kind, and 4 blue are of same kind. Now if somebody asks you how to arrange these many objects, so the answer is not going to be 12 factorial. Please understand, the answer is not going to be 12 factorial. In fact, it is going to be 12 factorial divided by 5 factorial, 3 factorial and 4 factorial. Multiplication of 5 factorial, 3 factorial, 4 factorial. This will be our actual answer and not 12 factorial. Why? Because you must appreciate the fact that in 12 factorial, each case must have repeated itself 5 factorial times due to green balls, 3 factorial times due to red balls, and 4 factorial times due to blue balls. Alright, so 12 factorial was an incorrect answer when not all the things are different, when some are alike. So if this is an incorrect answer, how are we going to get a correct answer? By dividing it with the correction. And that correction is 5 factorial because of this, 3 factorial because of this, and 4 factorial because of this. Alright, let me give you another example and let me ask you from you people only. If we have total 12 distinct objects, not all are distinct, total 12 objects, and out of these 12 I have 3 red balls and 2 yellow balls and 2 green balls. So in how many ways all the 12 balls can be arranged? So see, we have total 12 balls, out of which 3 red are of same kind, 2 yellow are of same kind, and 2 green are also of same kind. So this adds up to give us 3 plus 2 plus 2, 7. So remaining balls are 5, and these 5 are going to be what? Different. Alright, so the total number of arrangement or permutations of these objects is going to be 12 factorial divided by 3 factorial, 2 factorial, and again 2 factorial. Why 3 factorial? Because due to these 3 red balls, in 12 factorial, the cases would have repeated themselves how many times? 3 factorial times. Because of these 2 yellow balls, the cases would have repeated themselves how many times? 2 factorial times. And because of these 2 green balls, the cases would have repeated themselves how many times? 2 factorial times. Alright, so the incorrect answer to this question was 12 factorial, and when we have divided by the correction part, the correct answer comes out to be 12 factorial divided by 3 factorial into 2 factorial into 2 factorial. So this is what this theorem or this particular subtopic is all about. Alright, let me again explain you that total number of objects, if there are n, out of which p are alike of one kind, q are alike of second kind, and r alike of third kind, and rest all means out of n we have subtracted p, q and r, and remaining are all different, then the total number of permutations is going to be what? N factorial divided by p factorial into q factorial into r factorial. Because when the things would have been different, all the things would have been different, the total number of arrangement would have been done in n factorial ways. But we know that due to these p alike objects, the cases would have repeated themselves how many times? P factorial times. So we have to divide by p factorial, and because of these, the cases would have repeated themselves how many times? Q factorial times. So we have to divide it by q factorial, and because of these are alike, the cases would have repeated themselves how many times? R factorial times. So we have to divide it by R factorial also. Alright, so the incorrect answer would have been n factorial, and when we divided by p factorial into q factorial into r factorial, we get the answer of this part. Alright, our topic of permutations is completed and you people have got my point. Alright, so in the next class we will be taking a few examples, a few questions, and then we will move forward to understand the topic combinations.